So far, we've learned how to do stoichiometry problems for solids and liquids, which are easily measured in units of grams. As we discuss this chapter, it's much easier to measure the volume of a gas, so we're going to have to learn how to do stoichiometry calculations that involve volumes of gases. But just like every other stoichiometry problem, the first thing to do is read through the problem and figure out what chemical I know something about at the beginning and what chemical I'm trying to find out about. So as I read this problem, what volume of hydrogen gas? Well, it's asking me volume of hydrogen gas. That's what I need to know. Since it's a gas, I'm getting a few extra conditions to go along with it. I'm getting a temperature and a pressure for the gas. Will be produced if 25 grams of calcium hydride react. Well, that's what I know. That's my starting point for my problem. 25 grams of calcium hydride with excess water according to the following equation, and I've been given a balanced chemical equation. Like all stoichiometry problems, the first step is to get into units of moles if I'm not already given something in units of moles. And the grams of calcium hydride are not in units of moles, so I'm going to have to convert them. Grams in 1 mole is the molar mass, which I get from the periodic table, so I look up calcium and hydrogen, and I find that the molar mass of calcium hydride, which is CaH2, is 42.09 grams for every 1 mole. But I don't have 42 grams, I have 25 grams, so I'm going to set up a proportion to find out how many moles 25 grams is. And when I do the algebra, 25 divided by the molar mass, I find that I have 0.594 moles of calcium hydride. This is going to be my starting point for my stoichiometry problem for my BCA table. So I have 0.594 moles of calcium hydride, and according to the problem, excess water. And I usually start out with no product. I'm going to react all of that calcium hydride because it says in the problem it all reacts, so there is no calcium hydride left at the end. Then I'm going to use my coefficients, which represent mole ratios, to figure out the remainder of the change line. The calcium hydride reacts in a 1 to 2 mole ratio with water. Twice as much water reacts for calcium hydride. So if I multiply that amount of moles by 2, I get 1.188 moles of water. And there's extra water left over. There is a 1 to 1 mole ratio of calcium hydride reacted to calcium hydroxide formed. So I will form the same amount of calcium hydroxide as calcium hydride reacted. And that means I will have 0.594 moles of calcium hydroxide at the end. Also, I form hydrogen. There's a 1 to 2 mole ratio of calcium hydride to hydrogen. Twice as much hydrogen will be formed as amount of calcium hydride reacted. So I will form 1.188 moles of hydrogen, giving me 1.188 moles of hydrogen at the end. Now if I look back to the problem, what it's asking me for is volume of hydrogen gas. So I'm going to be focusing on hydrogen, which shows up in this section of the BCA table. But I'm going to have to take those moles of hydrogen gas and convert it into volume. We're going to do that on the next slide. So we figured out how many moles of hydrogen gas are formed. Now we're going to have to convert from moles of hydrogen gas to liters, something that is measurable. We have two options. First, we can use the molar volume of any gas, which is 22.4 liters in every 1 mole, to find out volume at STP. Because remember, this is only good, the 22.4 liters in 1 mole at STP. And then we'll use a PTVN table. And I'll show you the second option next. So option number 1. There are 22.4 liters of gas in 1 mole of gas at STP. But we don't have 1 mole, we have 1.88 moles, and we want to know the volume of that. So when I do the math, that says that at STP we'd have 26.6 liters of gas. So I'm going to fill out the table here. Would be 26.6 liters at STP, which is 1 atmosphere, and 273 Kelvin. And we want to know what the volume would be at 0.79 atmospheres and 303 Kelvin. So we'll set up a problem adjusting the volume for the actual pressure and temperature, 26.6 liters, and I will multiply by, we'll do the adjustment for pressure first. Pressure went down, and that causes volume to go up, so I need a fraction that will make my volume go up. So I choose 1 over 0.79. Next, my adjustment for temperature. Temperature goes up, and that causes volume to go up. So my temperature fraction should be bigger than 1, 303 over 273. And if I do the math, what I come out with is 37.4 liters of hydrogen at the conditions I want, 30 degrees Celsius and 0.79 atmospheres. The other way to do the problem is to utilize the ideal gas law, or those values of R that we found out the other day. I gave you 2 choices, and we want to select the choice that corresponds to pressure in units of atmospheres so that we match all of our units. And for atmospheres, the gas constant is 0.0821 liters atmospheres for every 1 mole and every 1 Kelvin. And so I'm going to set up a proportion here. So we do not know volume, that's what we're trying to figure out, but we know that the pressure that we want is 0.79 atmospheres. And we know that the moles that we have are 1.188 moles. And we know that the temperature we want is 303 Kelvin. So we're going to do some fancy algebra here. We're going to cross multiply. And so I'm going to multiply 0.0821 and 1.188 and 303 to get 29.55. And then I'm going to multiply 0.79 and x. And then divide both sides by 0.79. And the volume that I come up with is 37.4. So as you can see, it does not matter which method you use. If you use the molar volume at STP and then adjust to different conditions using a PVTN table, or you go ahead and you use the constant that's already been adjusted for pressure and temperature, also known as the ideal gas law, and use that method. We got, just whichever method we use, we got the same volume either way. So there are 37.4 liters of hydrogen formed in this reaction.